During the course of making the 6502 emulator that I was doing in the previous video, by the end of it I'd made quite a few mistakes and a lot of the code I'd written probably wouldn't work, and I thought that would be a good opportunity to integrate GoogleTest and actually write some test cases for some of this stuff, because a processor seems like the kind of thing you should be able to test really easily because it's got a set bunch of instructions and they do a set bunch of things. Since the last video, I've just rejigged the project a little bit, moved the code that I wrote for the emulator out into its own library. So I made an own library for the emulator, and that's just got a header file with the code that we wrote for that. It's not got the main method in, that's the big difference there. So it's not really a huge difference, and the main method has just gone into its own executable, and it's just the main method now with the include, so it just includes the file. So I've just split the executable and the 6502 library up into two. That's the way I prefer to do it, just because you probably got an executable that you're working on that's actually using the emulator, and if you're using GoogleTest you probably have another application as well that's just running the GoogleTest. In this case I'm only have the one exe anyway, so we're just going to put the GoogleTest into here. So the other thing I did then was I followed Google's instructions on how to get GoogleTest working in a CMake project, which is this, and I just followed these instructions here which said do this and put this in basically, and that's what I did, and it works. And this kind of now when I run the CMake project, actually automatically downloads from GitHub the GoogleTest library, sticks it in here, and then you can actually add it as a link library to your project. So I've added it as a link library into this executable part, and as you can see I'm also linking in the library that's got the emulator that we wrote. So really what I want to do now is convert this application, which is this one here. This really was a test application at the end of the day. I really just want to convert this into a GoogleTest application, and then we'll start testing it. So one of the things it says to do, or one of the things you can do with this, is it's got a GoogleTest main, and that's just like it's just a tiny little main app that just gets GoogleTest running. So I'm going to copy all that out and just paste it into here in place of our old test application there, and I'm just going to if zero this out for now. So in theory what this does is just replaces our application that we wrote with just the GoogleTest like boot up sequence. So if I just build this, it builds. So because this application's got a dependency on GoogleTest and the emulator library, so it should build those both. And then I'll set this as the startup application. And then this in theory should just run GoogleTest and actually not run any tests, I think. Yep, there it is. So it's just not running, it's run zero, just telling me it runs zero tests. So that's exactly what we wanted there really. That's we've integrated GoogleTest into the application and it doesn't run any tests at all. So that's a good start. And then for the actual getting the tests to work themselves, the docs here has got I think it's primer, and it tells you how to write tests and stuff like that. But I'm going to skip right down to, it's got simple tests, but I'm going to go down to these test fixtures because I think I do all of mine as test fixtures. You can do them, you can look up the simple tests if you want, but the test fixture is just a way of making a test that has some preset data, which we might want to do, but it's so easy to do. I find you might as well do all your tests like that, even if they don't have data. So the first thing I want to do is I want to add just a separate CPP file that's going to contain a bunch of tests. So I'll add that to the CMake file. So we've got our main in there. Just going to stay the way it is. We'll just do it. We'll just call it test for now because we're just trying to get this thing running. There we go. So I've just put that CPP file in the same folder as the main, and I've told CMake to compile that when we build this exe. So really now all I need to do is rerun the CMake to just regenerate the project. So CMake's just rebuilt this project, and I'm going to reload, and there we go. So I've got my little, so there's my CPP file ready to accept some Google tests, and I'm just going to cut our old program. So that's the boot up sequence for this. I'm just going to cut our old program and put it in there because I'm going to want that in a minute, because that's kind of forms the start of one of our first tests. So now I'm going to follow the instructions on how to make a test. I think we have to include GoogleTest or G-test. And then it says derive a class from testing test. There we go. So I think that's the first place. This is where we get the little fixture. So I'll just call this M6502 test 1, something like that. And we derive from that. So that's created the test fixture. If necessary, write a default constructor or setup function to prepare your objects for each test. A common mistake is to spell setup as setup with a small u. Oh God. So I think what they want is they want us to have this. They want a setup, and there's also a tear down. So that's, yeah, tear down. So there's also tear down there. So that's just a little test fixture. I think that is really all you need, and you don't really need the setup and tear down if you're not going to do anything. But in here, if we do decide to have a CPU that we want to test with, we can set it up and tear it down every single time in here instead of having tons of code in the tests like we've got here that can do that. So in fact, we could actually do what it says, and we'll have a CPU in memory, and we will reset the CPU every time we start in there. We also need to include our actual 6502 library now. So yeah, in here is just the code we wrote in the previous video that just emulates. I think we've got 4 instructions working. So yeah, so that's our little test fixture. And then we just define a test using test F, and the F stands for fixture, and we give it the fixture name and we give it a test name. So it's very macro based, this testing library, and I think most of the ones I've seen are. So that's it. So what's our first test going to be? We probably just want to do what this one did here. So I think you do them like this, and we'll call this, this one is, we'll just call this run a little inline program. So in theory, this doesn't look like it's going to compile. Oh, cannot access private member. Oh dear. It's because everything's private in classes for some stupid reason in C++, which was, I think that was a really dumb idea, but that's what they went with. So there we go. So we've got basically we just took our little test program that we had in the previous video and we stuck it inside a test. We haven't really done any proper tests yet, but at least we're going to know that we're going to see if this is actually going to run. And oh yeah, there it is. Oh, and look, we're actually getting, like, it's printing output instruction not handled 0. So there clearly is actually already something wrong with this, that it shouldn't be doing that. I mean, I think the program we said we were going to run was going to be fine. Maybe we ran too many cycles or something like that. So that's saying okay, but clearly that test isn't okay. So we can probably do better than that. The theory with this was that at the end of it, the A register would end up with the value 84 in there. So really, that's what we want to test in here. So I think they have, I think everything starts with expect, and we can have expect equal. Is that right? Yeah. So this is how you verify the test. So the CPU A register, we are expecting to be 84 at the end of this test. So this isn't a super great test, but this is just the code we had, so I'm going to run with it. Let's see if that works. So that's good. And just to verify that this is like working, if I said that I expected the A register to be 86, what do we get? Ah, failed. There you go. And it actually tells you it's really good. CPU A, which is 84, 86, which is 135. It's even like converting it to decimal for me. Expected equality of these values. There we go. So that is already pretty cool. But I don't want to do these tests where I'm like doing a JSR and a load immediate and all this kind of stuff. I really just want to test one thing at a time. And that's what you'd really do with very small tests like this. So we could write a test for every single instruction that we're going to run in the program and every single variant in a way that it could run and all the things that we know could happen and stuff like that. So for now, let's just say LDA immediate can load a value into the A register. So there you go. So we just name our test in a way that it really tells us what it's going to do. let's do inline our little program like so. And we only need to execute 2 cycles for that, I think. So the other thing I like to do as well is I just say given, basically we say given when then. So you can see kind of like, that's usually the format for these kind of tests. What you're basically saying is given this set of data, when this happens, then I'm expecting this to be true. And all the tests will probably take that format. So let's just check that's fine. So there we go. So that's a good test now, and we're not printing out that, oh, something that, you know, there was like a 0 was found or something like that. So this is a bit weird because we've already got this working, and there might be other like criteria for this running, this little program. There might be other ways we have to run it to make sure that it does work. But I'm just going to run with this for now. So really what we'd want to do then is we'd want to start testing individual parts of this program. We had load LDA from ZeroPage as well. So we could test that one. So LDA ZeroPage can load a value into the A register. So let's test that one. ZeroPage. So we take the address in the ZeroPage, and then we're going to shove into the ZeroPage that value, that address, sorry, 42, and then we're going to put like 37 in there. So in theory that should, we need 3 cycles to execute that one. In theory that should give us 37 in the A register. So let's give that one a go, and then hopefully we've got 2 tests that work. Yeah, so we're down to 2. So now we just keep going. And what else have we got in here? Oh, we had load ZeroPage X. That was with an X offset. Can load a value into the A register. So what we could do with this one will probably need a couple of tests, because this is one of the ones I think I did wrong in the previous video. So because we've got access to the internals of the CPU, we can actually just fudge the X register, and we can say, so we can say it's like, let's just say it's 5. So we're going to say the X register is 5, and then we're going to load ZeroPage X. So this loads a value from the ZeroPage and then offsets it by a value in the X register. In fact, let's just check is correct. Is it 52? The address to be accessed by an instruction using ZeroPage addressing is calculated by taking the 8-bit ZeroPage address from instruction and adding the current value of the X register to it. Yeah, it should take the value 42, add 5 to it, and then read from the value in memory at 42 plus 5, which is 47. So in theory now, this also does the same thing, because we've got our 5 in our X register. We just fudged that, and we fudged a little inline programming. Let's see if we get that one working as well. Oh, it's all gone wrong. It's all gone wrong. What happened there? Did we need another cycle to... Yeah, we needed 4 cycles. So actually, there's a problem already, is that if we don't execute enough cycles, we get stuck in a loop. I should have put 4 on this one. Right, let's try that again. There we go. So ZeroPage X can load a value into the X register. Now, this is the bit in the last video where I actually didn't do this fully correctly, and now we can write a test that won't work, and then we can fix the program. So it says the address calculation wraps around if the sum of the base address exceeds FF. We repeat the last if we repeat the last example but with FF, the X register accumulator will be loaded from 7F and not from 017F. I mean, we could just write this in as a test now. So LDA ZeroPage X can load a value to the A register when it wraps. So yeah, so we're going to have to do another test for this. So they reckon, let's do their test. They want to load 80 into the yeah, load 80 into there, and let's have FF in the X register. And are we going to check their math, or are we just going to assume this is correct? So we expect it to read from 7F, which is this value. So let's run this test. So I don't think I handled this in the previous video. I didn't handle this. Oh, what's going on there? Is this wrapping automatically without me having to do it? Oh, that's interesting. So here's a weird thing. It's like I thought that this wouldn't work, but somehow the code that's been written does actually work, even though I've not actually handled this. So we could actually go in and have a look at this test. Now that's the other good thing about having these tests now, is that you can actually just debug them. I was definitely expecting this to fail, and it's not. So why did it not fail? So let's go in and have a look. So we go in Fixture instruction, which is should be load ZeroPage. We get the ZeroPage address, which is 80. That's what we said, and then we add the X value, and that gives us 7F. Now I think this is working because we actually are using an 8-bit type here. If we'd have used a 16-bit type for this, then this would have not actually worked. So actually, the one thing that I thought wasn't going to work actually does work. Oh, and we're not checking, we need to check the status registers as well. So that's another thing. Yeah, because the LDA instructions can set the flags. So we really need to write some tests for that as well, to make sure that that's working. For this one, we can test the value of the 0 flag. We are expecting the 0 flag because the value that we loaded in is not 0. Sorry, set if A is 0. So this should be false. I think there's an expect false. I think we can do that. There we go. And there's a negative flag as well, which is N. And we want to set if bit 7 of A is set, and that's not going to be set on that. So that should be false as well. In fact, these should all be false in all of our tests. So let's just run that and make sure that still works. So now we're starting to test that we're getting the flags correctly. In effect, we really should be testing all of these flags because it says these are not affected. Yeah, it's saying the other flags are not affected, so they should just be whatever they were at the beginning. So I will actually going to take a copy of the CPU. That's weird. It's something you can't do normally, isn't it? CPU copy. Let's call it CPU copy. I'm going to copy the CPU, and these other flags should not change. So the carry flag, this is expect equal now. Equal. Carry flag, input label should be changed. Decimal flag should be changed. Break command should be changed. Overflow flag should be changed. Is that correct? C I D B B. There we go. So same thing on that one, and same thing on all of these at the moment. Look at this. I mean, we could actually write a little function to do that test, but let's not do that for now. So let's make a little copy of the CPU every time we run this program, and let's make sure we're still running. I was hoping to see a failing test on this, but it's not happened. What's happened there? So we've actually got a failure. Why have we got a failure on that? That's interesting. That's the first one. LDA immediate can load a value into the A register. Which one of these is failing? So the negative flag is being set on this one. So have I got that wrong? Oh, yeah, I did. I actually got that one wrong. So this one is actually being considered as a negative number. So if bit 7 is set, if bit 7 is set on the value, then that negative flag should be set. 0, 1, 2, 3, 4, 5, 6, 7. So there we go. So actually, that should be true on that one. Actually, there we go. Let's try that again. And there we go. So we've now got 4 tests running. We're checking the status flags. We are checking the value we expect in the A register. What we're not checking at the moment is we're not checking whether it took the correct number of cycles. So that is something that we could also actually do here. And to do that, what I might do is actually from here, we could actually return the number of cycles that were used. So because the number you pass in and the number it uses might be more, I don't think it'll ever be less, but it might actually be a bit more, because this might go to -1 depending on what happens in here, like if it has to do 3 or 4 cycles down here. So this is what I might do here is I will return, just for now, I'm just going to return -1 from that. And then I am going to also test so I'll actually store the cycles used from each one of these tests, and then we can actually make sure that we use the correct amount, 2, 3, 4, and 4. So let's go back. So cycles used 4, let's use 2. Cycles used for, so which one is the number one? Cycles used for 0 is 2. Cycles used for ZeroPage is 3. Yep, that's right. Cycles used for ZeroPage X is 4. So which one are we using? You don't really care how we're supposed to do. And this is the same one that perhaps is the same as the ZeroPage one. Doesn't really matter. So let's run that. Oh, it's because I'm returning unsigned. Oh, that needs to be assigned. Instantly, I've found a problem here. So instantly, this can't return a U32. We now need an S32 because it might consume more cycles than we wanted. So let's define a using for that. Right, you're going to let that compile now. Signed unsigned mismatch. Where are we? Oh, that's because because that is, why do you think? Oh, because now I've got all these as U32s. Okay, right, here we go. I've got quite aggressive compiler options on to catch these kind of things. These would have been errors as well, so there we go. So right, we've now got our failing tests because we haven't actually returned the number of values that we use. So cycled use is -1, we expect whatever. So we've got our test working. Now we can actually write the code that makes it work. So let's go in here. And where was our function? So at the end of this, when it's come out, we actually just want to, I think we actually just return cycles, because this will either consume down to, oh no, we need to take a copy of what it was when we came in. So let's do that. I don't know what to call this. This will be cycles requested. So yeah, so we just save that on the way in, and the number of cycles requested. So I think this will be the number of cycles requested and subtract the cycles that were left, and that's the number of cycles we actually did. Because if this went minus, we executed too many cycles, this would be, say we executed 10, we actually requested 10 but we executed 12. This cycles is going to end up at -2, so that will add 2 onto it, and if it's at 0 it will do nothing anyway. So in effect, I think this is actually just giving it a name there. Right, I think, and again, we've got the test for this now, so we're going to know if this works or not. And there you go. So we're now testing that not only are we running the instructions, are we running the correct instruction, are we using the correct number of cycles, are we setting the processor status flags correctly afterwards. And none of these, well, when we get to JSR, I think this is another problem. In fact, I made a note of it here. We need to make sure that the stack pointer gets moved about correctly, because this will affect the stack basically. So that'll be the next thing to do on this. So I'll probably leave it there for now, but I'm going to continue with this. But that just goes to show like what you can actually do with GoogleTest. Like setting it up is probably taking longer than writing these tests, but this is just like, you can see you could end up with an absolute buttload of tests for this, because this is just testing, I think this is testing 3 instructions that are working correctly. I think we have fully tested those 3 though. I'm not sure there's anything else we'd need to do on those to test those. Like when we get down to these, there's some weirdness here because some of these take a different number of cycles depending on if the place they access in memory is different. So there's stuff to do there. But now this is in and it's part of the program, we can actually start making this like more robust. So really that's just an introduction to GoogleTest basically, and why you'd want to integrate that into a program like this, because as you can see, we've already got like quite a lot of testing going on there. It allows you to later on not only verify that it's working and have confidence in that it's working. Like I wasn't confident that this ZeroPage X was actually working. I was like, oh, it probably doesn't work, I need to fix it. And by doing this, I've actually found out that it did actually work, and I didn't know that. But so the confidence it's giving me is high. I have high confidence that these 3 instructions that I've written are actually correct, and they're actually doing the correct things in here. Yeah, so it's basically just a primer on GoogleTest and how you get all that set up. And I might continue with this in another video and do some more of these instructions and promote this to GitHub, and maybe we'll get this processor up and running at some point. Who knows?